Okay, so welcome back. We had last time finished with the following theorem and given a proof or at least a sketch of a proof. Okay, today we'll see another one which will have some kind of different elements in it. So this is the Cayley-Hamilton theorem. Okay, so it said let A be a matrix, n by n matrix, and PA of lambda, the characteristic polynomial. Okay, so this was PA of lambda is the determinant of A minus lambda I. Okay, so it's known that this is a polynomial in n variables, so it looks like lambda to the n, and it happens to be monic, so an minus 1 lambda to the n minus 1, all the way to a naught. Then, so the statement, that's just an aside, the statement is that PA of A is equal to 0. So in the sense that A to the n plus an minus 1 a to the n minus 1 all the way to a naught I is equal to 0. Okay, so the same relation, or the same polynomial equation which the eigenvalues of A satisfy is also satisfied, suitably interpreted, by the matrix itself, right? So now this is not equal to 0 as a number, but 0 as the zero matrix. Okay? So we saw a proof kind of which used some analytic tools, and now we're going to do a proof that only uses linear algebra. So let me make two starting remarks. Okay? We saw the first one in the last lecture. So this said that every non-zero linear transformation on a complex vector space had an eigenvalue. Okay, this was the largest difference for us between working, say, over the real numbers or working over the complex numbers. Okay, so the method of proof that we're going to use for the Cayley-Hamilton theorem is going to be to reduce it to proving this theorem for upper triangular matrices. Okay, so I want to first give a second remark, which kind of characterizes what the upper triangular matrices are doing. So now again, let T from V to V, now this works over any field, be linear transformation. Okay, so a matrix representing T is upper triangular. A similar statement will work for lower triangular matrices. So a matrix representing T is upper triangular if and only if there exists some basis, V1 up through Vn, of V, so that T of V sub k is in the span of V1 up through Vk for all k. So let me make this just a little more explicit. We're saying T of V1, for example, is in the span of V1. So in particular, T of V1 is a constant times V1, or in other words, V1 is an eigenvalue. Okay? Well, T of V2, we don't know that it's an eigenvalue, but we know that it's in the span of V1 and V2, okay? And this continues, okay? So you kind of start with an eigenvalue. The next vector in your basis is limited to be in a two-dimensional subspace, a three-dimensional subspace, and so on. So let me draw just a corresponding picture here for R3. Let's just say this is V1, V2, and V3. Here's T. Okay, so we know that this matrix in the VI basis is upper triangular. So I can even make this explicit, so it looks like star 0 0 star star 0 0 oops, star star star. Okay, so if I plug in v1 into this matrix, that's like looking at 1 0 0, and this is star 0 0. Okay, so v1 is an eigenvalue, so it gets sent to some v1 here will go to some multiple of itself. Okay? Again, if I plug in 0 1 0, okay, so 0 1 0, this is going to star star 0, or again, the stars can be any variable. Again, this is saying now that it's going to something in the v1 and v2 plane. So this vector, corresponding to v2, is forced to go somewhere in the xy plane, or the v1, v2 plane. Okay? It can go anywhere in there, but it might, in fact, land on, the vector or the line spanned by t of v1, but it's somewhere in here. Finally, v3, I won't write it down, but if you plug in 0 0 1, you'll just get this last column, which is completely arbitrary. Okay, so t of v3 can go anywhere. And that's the general picture, right? So if you have an upper triangular matrix, what you're going to see is this sequence of vectors. The first one is an eigenvalue, the second one is in this two-dimensional subspace, the next one's in this three-dimensional subspace, and so on. So this is really kind of the geometric way to think about what these upper triangular matrices are representing as linear transformations. Okay, just a very useful picture to have in mind. Okay, so let's do a lemma first, which says that if we're willing to work over the complex numbers, then everything is similar to a upper triangular matrix. So I've kind of used this before without proving it, so let's prove it now. So V is going to be a complex vector space, T from V to V linear transformation. Then there is some basis, so that the matrix for T, okay, with respect to this basis, is upper triangular. Okay, so, or in other words, any matrix which represents T is going to be similar to an upper triangular matrix. So let's prove this. The proof is going to follow very quickly, actually, from the fact that every complex vector space, this linear transformation is going to have an eigenvalue. Okay? So what's the proof? So we induct on the dimension of V. With the case of V just being dimension 1, follows immediately. Okay? So what do we know? So we're going to assume it for, all vector spaces of, complex vector spaces of dimension less. Well, we know that we have an eigenvalue. So we have an eigenvalue, lambda, in C, okay? And what this means is that if I look at the new operator, t minus lambda I, this will have a non-trivial kernel, okay, for some lambda. Okay? So by the rank nullity theorem, since this has a non-trivial kernel, we have that the dimension of the image of t minus lambda I is less than the dimension of V. Okay, so we have V in this linear transformation which takes it to itself, and what we know is if we look at t minus lambda I, we get a subspace of smaller dimension. So I'm just going to call this U. Okay, so now we claim that U is T invariant. Okay, so in other words, T of U is strictly contained in U. Okay, so why is this? Well, let U in U, okay, so U is equal to T of V minus lambda V by assumption. All right, we're assuming that we're taking something in the image of T minus lambda I, so we can write it as a difference of T of V minus lambda V for some V. So I should say there exists a V here. Then T of U, well, by linearity is T of V minus lambda V, which is T of V minus lambda T of V. Okay? So in other words, T of U is in the image of T of V under T minus lambda I, so therefore T of U is in U. Okay? So we know now that we have this subspace, which is of smaller dimension, and whatever this linear transformation does, it keeps it inside of itself. Okay? So now by induction, we can assume that U has some basis, which I'll call U1 up through UM, so that T of UK is in the span of U1 up through UK for all K. Okay, so in other words, with this matrix, or with respect to this basis, U is upper triangular. Okay, so this is what we know. Well, now we can just extend this to a basis for V. So extend U1 UM to a basis for V. And we claim that this works. Okay, so I'll just say this is U1 up through UM, and then let's just say V1 up through Vj is our new basis. Okay, or is a basis for V. Well, then T of Vj, this is T minus lambda I of Vj plus lambda I of Vj. So in other words, we have something that is in U, okay, so it's in the span of U1 up through UM, plus something that is just Vj, okay, so a multiple of Vj. So therefore, T of Vj is in the span of U1 up through UM and Vj. And now, so it doesn't even matter how we order the Vi through Vj at all. No matter what, they're going to be in the span of just the basis for U plus the additional vector Vj. Okay? And that's the proof. Okay, so therefore, with respect to this basis, maybe we'll just add this on as a corollary. So in the basis U1 up through UM, V1 up through Vj, T is an upper triangular matrix. Okay, so with this in hand, let's prove the Cayley-Hamilton theorem now. Okay, so we're going to prove Cayley-Hamilton version 2, okay, or version 2 of the proof. So in the last proof, we saw that if the Cayley-Hamilton theorem holds for a matrix A, it holds for any matrix similar to A. So by the last result, we can assume that the matrix that we're dealing with is upper triangular. Okay, so we can assume that A is an upper triangular matrix, just prove Cayley-Hamilton here. Okay, well, notice now that the eigenvalues through lambda n, so this is our matrix A, the eigenvalues are going to be along the diagonal of A. Now, what I haven't exactly said in the last proof, but I think it's fairly believable, and you can also, a more careful proof of the above will give this for you, is that you can assume that the eigenvalues along the diagonal are in any form that you would like. Okay? So in particular, there may not be n distinct eigenvalues, where n is the size of the matrix, n distinct eigenvalues. Okay? So in other words, some of these diagonal terms may be the same, but you can assume that they're grouped together. So you have like some collection of lambda 1, some collection of lambda 2, and then some collection of lambda k. Okay? So you can switch the order of the diagonal so that all of the similar eigenvalues of the same value are next to one another as you go down. Okay, so now, so the eigenvalues here are lambda 1 up through lambda k, okay? And the characteristic polynomial that's determinant of a minus, say, ti, so I'm going to switch just to not have too many lambdas, okay, is precisely lambda 1 minus t to the m1, lambda 2 minus t to the m2, up through lambda k minus t to the mk, for some natural numbers m1 up through mk. Okay, so I'm just counting the multiplicities of each eigenvalues. Okay, so now the expression that we have to look at are, the expression as a product of matrices. Exactly lambda 1i minus a to the m1, lambda 2i minus a to the m2, up through lambda ki minus a to the mk. Okay, so now the claim is that this is equal to 0. And I will give, the idea of the proof of this. So what do we need to show? Well, remember, this is just some matrix, okay? And what we'd like, or you can think of this as a transformation. So what we're going to show is that for all the basis vectors, right, and we've chosen a specific basis, so that's an upper triangular matrix. For all these basis vectors, this expression evaluated, so if we evaluate the above at v sub j, okay, then we get 0. Okay, so in other words, we take this power, it looks like lambda 1 times identity matrix m1 up to here. Think of it as a linear transformation, plug in a basis vector, and this should be the 0 vector. If you've done that, that means that this is actually the 0 matrix. Okay? So let me give you kind of the idea of what this looks like, okay, and why this is true. Okay, so why does v1 go to 0? Okay, so let me write down this expression. Okay, so first, what does lambda 1i minus a look like? Well, I know A was an upper triangular matrix, and it had this block of lambda 1s down the identity. So it'll look something like a bunch of zeros. Then we have lambda 2 or minus lambda 2s, and then everything else will just look like A. So in particular, I have a column of zeros, okay? And this column is going to be preserved if I raise this to a power, right? You can imagine composing this matrix m1 times preserves this first column, okay? So what this means, well, let's just look at, I won't write down all the expressions, but we'll go to the matrix to the m2, then, lambda ki minus a to the mk, and then we're plugging in v1, all right? Now these are all upper triangular matrices, so v1 under each of these transformations is just going to a multiple of itself, okay? On the other hand, since this last matrix had an eigenvalue, this was the matrix with the eigenvalue of lambda 1, so in particular lambda 1 times the identity minus it had this column. So v1 goes to a multiple of itself. Okay, and you know exactly what the multiple is. It's something like lambda k minus lambda 1 for all k. So this goes to a multiple of v1. And then at the last stage, this goes to 0. Okay, because you've chosen the lambda 1 eigenvalue. Okay, so a similar argument works for all vi between 1 and m sub 1. Okay, so the one claim, which I won't justify, is that if I look at lambda 1 I minus a now to the m sub 1. So remember, so in this last argument, I didn't need to use this power at all. Okay, it just came from the fact that I took one lambda 1 minus I and I had a column vector. This power comes in. Okay, so again, this looks like 0, and then the negative lambda 2's, and so on. This might be anything, okay, the blocks above these zeros. However, when you raise it to the m first power, which is just the number of 0 terms here, what you'll end up with is a whole block of zeros, exactly an m1 by m1 matrix, and then this continues. And then you you lose control, right? You don't know what happens in all these other terms, but you're guaranteed a block of zeros. This is essentially something that we proved using the Cayley-Hamilton theorem in the last lecture as an application. Okay, so what I need is that when I take this matrix, which is upper triangular and zeros along the diagonal, the m first power of it is just the 0 matrix. But this is also something you can just do with computation, okay, of multiplying matrices out. So anyways, you get a block of zeros, okay, in this first term. And now, what happens if you take vk for 1 less than or equal to k less than or equal to m minus 1. Or sorry, m1. Okay, so we want to know kind of what to do with the first vectors or in our basis that correspond to this block. Okay, well, what happens is, again, all of these matrices over here are upper triangular. So vk, once you multiply them out, you have no idea what they do, but you know that they go to something in the span of v1 up through vm. Actually, v1 up through vk, but it suffices to just do v1 up through vm1. Oops, and I realized this should not be a power, right? That's just a matrix. So anyways, this v sub k is going to something in this span, and then this last matrix, these are all zeros now, so this just sends all of these vectors to 0. So this goes to 0 by the last matrix, or the first in the matrix, last in the composition. Okay, so that's essentially how that goes for the first vectors. Okay, so maybe I'll just say how you do the second block. So if you have something, if you have vk1 less or equal to k less than or equal to m2, what you'll end up with is two vectors. The first one looks like this block of zeros, which is m1 by m1. The second one won't have this, but it will have a block of zeros, which is m2 by m2. Okay, the same exact argument for the first matrix will give you a block like this. Okay? And now what you're doing is you're plugging in v sub, let's say, k for m1 less than or equal to k less than or equal to m2. Well, the first, this will go to something. Again, it will go to some span. It's going to go to v sub k goes to something. Since these are all upper triangular again, something in the span of v sub 1 up through v sub m2. Okay, that's just what you know from upper triangular. Now you apply this matrix. Okay, so this was the m second power, corresponding to the second eigenvalue. And what this will do is that this second matrix, so the matrix on the right, turns it into something in the span of V1 up through Vm1. Okay? And that's because what this is doing is exactly killing off all the later terms, right? This corresponds to the Vm1 through Vm2 block, and that goes to 0. Okay, so something is just in the span of the vectors between V1 and Vm1, and therefore what this means is that the first matrix sends this to 0. Okay? By the same argument as above. And that's how essentially this inductive procedure works, right? So you're going to have a block of zeros for this matrix, a block of zeros here, continuing till you get a block of zeros, and then any basis vector, what these matrices will do is essentially chop off the last, some k vectors, or some number of vectors in the span, until at the very end you just kill off everything and you get the 0 vector. Okay? So it's a little sketchy, but that is really the idea of what's going on there. Okay? So that, I'm going to say, is proof of Cayley-Hamilton. Okay? With a few details missing. Okay, so now I'd like to change topics and go essentially to a topic that's going to occupy us for the rest of the class. Okay? So this is now chapter 5 in the book, so we're going to see inner products and inner product spaces. Okay, so what this will let us do is give us a little more geometry in our linear algebra. We've been seeing it with the determinant and the fact that we have defined what an area of a parallelogram is, or more generally the volume of a parallelepiped. Well, now we'd like to, get into what is the length of a vector, okay, or the angle between two vectors, okay? This is something that we want to add. It also means that we're going to essentially only work in R or C, okay? So this is now going to be F for the remainder of the course. And usually I'm going to be thinking about the real case, but I'll say, what you have to do to make adjustments in the complex case. Okay, as we've seen with when you do spectral theory, you want to use complex matrices, so it's good to have both sides here. Okay, so let's just think of first what the length of a vector is in Rn. Okay, well, this is just, there's a distance formula in Rn. So like the Euclidean distance between the 0 vector and the vector v, okay, or the endpoint of the vector v. And this is given by square root of x1 squared plus x2 squared, right? This is precisely the distance in R2, okay, or the length of the straight line between 0, 0 and x1, x2, okay? So we think of this as the norm of the vector x, okay, is precisely this length, okay? So you can think of it as norm is a function which goes from your vector space, outputs a real number, okay? And actually it outputs a positive number. You can do the same thing in Rn, okay? So the distance between the origin and a coordinate in Rn is just, well, I'll write this way, x is equal to the root of x1 squared plus x2 squared up through xn squared. Okay, so this is my vector x1 up through xn. Now, of course, this interpretation as the distance in Rn depended on a choice of standard basis, right? So I was setting, if this was my vector x1, x2, I was setting a standard basis E1, E2 and having each of these be length 1. Right? If I had chosen a different basis, then of course these coordinates would be different, and I would, the distance would no longer be equal to this quantity. This doesn't stop me from defining this as a function, okay, but you would have to reinterpret the geometric picture. Okay, so let me just say this, we're going to call the norm of x, okay? Now this norm, so the norm of x, in this case, happens to be induced by an inner product. Okay, which I won't define. Well, we have actually already seen it because I introduced orthogonality earlier in the course. Okay, but what I mean here is that this is now going to be a function which goes from v cross v to r. Okay, so you can think of it as inputting two vectors and outputting a real number. In this case, you just send x, y, written again in coordinates to be x1, y1, up through xn, yn. Okay, so this is the standard inner product on Rn. You've probably seen this before in R3, where it's called the dot product. Okay, and the norm of x is by induced, I mean that you obtain it by looking at the inner product, and in this case taking the square root of the inner product of x with itself. Okay, so somehow this norm comes from this inner product. Okay, so let me just say how you would do this in Cn. Okay, so here I'm drawing a picture of C. We have x plus iy. The norm of a single complex element, okay, is equal to x squared plus y squared. Okay, we want our norms, even in the complex numbers, we'd like them to be real numbers. We want to think of them as measuring some sort of length. Okay, and this also happens to be equal to z conjugate, okay, which is just, so if this is x plus iy, this is x plus iy times x minus iy. Okay, so you multiply these two complex numbers, and you'll get the real number here. Okay, norm of C. Okay, you do essentially the same thing for Zn. Okay, so you get the norm of Z, now for Z, an n-tuple of complex numbers, is just the norm of Z1 squared plus the norm of Zn squared, and then take the square root. So it exactly matches the real case in this definition, but you have to be a little careful because you're really, when you're looking at one of these numbers, it's really the norm of a two-dimensional vector in R2, if you want to think about it that way. Okay? This also comes from an inner product. Okay, in this case, this is just going to go from Cn cross Cn to C. To find analogously the inner product of two vectors in Cn, well, again, we want it to match, you want the norm to be equal to the square root of the inner product of a vector with itself. So you take Z1 W1 conjugate plus Z2 W2 conjugate up through Zn Wn conjugate. Okay, and again you'll get that if you take the square root of the inner product of ZZ, you'll get the norm of Z. Okay, so we've defined some functions on Rn. Okay, so I would like to know what the properties, and really you can think the inner product is the more fundamental of these properties because it determines the norm, okay? In some cases, it turns out that you have vector spaces that naturally admit norms that don't come from inner products. In this case, the one that we have does. So let's think of the properties of just the inner product, and that will kind of correlate to properties about the norm. So the first one is that, well, x, if I take the inner product of x, y, this is equal to the inner product of yx, as long as I conjugate. Okay, so a lot of these formulas will involve conjugates for the complex numbers, and then you can get rid of them if you're thinking about just real numbers. Okay, so that comes straight from the definitions. The second one is linearity. So if you have alpha x plus beta yz, this is equal to alpha of xz plus beta of yz. For appropriate scalars, alpha and beta and x, y, z vectors. You also get that if I take the inner product of x with itself, it's greater than or equal to 0, and I get that it's equal to 0 if and only if the vector x is 0. Okay? So it assigns a non-trivial length. This inner product assigns a non-trivial real length, okay, to every non-zero vector. So maybe I should just notice that even for Cn, z is in R, okay, automatically by property 1. Okay, so if you have this function which satisfies this property, then if you put in zz, it's going to be, the inner product of it will be equal to its conjugate. That means it has to be a real number. Okay? So now, so the definition for V, to say real or complex vector space, okay, an inner product on V is just a function which goes from inputs to vectors, outputs, I'll just go to F, okay, so it's R or C. It's a function here satisfying 1, 2, and 3. Okay, and then you have the induced norm, which goes from V to R, just takes x to the inner product, to the inner product of x with x. Okay? So let's do some examples of this. Okay, so the first example that so we saw one example, the most important example, right, Euclidean inner product. You can also take kind of a weighted version of the usual inner product. Okay, so I'll just do this on Rn. You can do it on Cn as well. So you can take Rn to R and send x, y to A1, x1, y1 plus A2, x2, y2 up through An, xn, yn for A1, A2 up through An positive numbers. Okay, so what you're essentially, is at least if you look at the induced norm, is like a weighted length. Okay, so you have your vector, you have, your 0, x1, x. Looking at the weighted norm, so the weighted norm of x is root of a1 x1 squared plus a2 x2 squared. So these are, you can think of them as weights assigning, how much you value the distance in the x direction versus how much you value in the distance in the y direction. If you consider them equally, it's just like a multiple of the usual Euclidean distance. But you could say, that A1 is 100 and A2 is 1. And, this vector looks longer, but in this weight is considered much shorter than this one, okay? Because the y value doesn't count for much, but the x value becomes huge. All right, so there's a lot of different, that gives you a whole continuum of different inner products, okay? Here's another interesting one, which is if you take v is continuous functions on minus 1, 1, okay? So we saw before, earlier that, this defines a natural vector space where you are just adding functions or multiplying them by scalars, okay? Then the inner product of them is just the integral from -1 to 1 of f of x times g of x, okay? So notice this vector space is, infinite dimensional. It doesn't have a finite basis, okay? And you can think of this as kind of like a continuous version of the inner products above, right? So here, I guess I'll put it here. So here you're looking at the products of these values, and then, you're multiplying them together and then summing them all up. Here you're taking the product of the values and summing them up, but now they're continuous functions, so instead of summing, you just integrate, okay? So therefore the corresponding norm, the size of a function, is just the integral of f squared dx, or square root of that. Okay, so here's another example, all right, which we could take the space L2, which was square summable sequences. Okay, so we think of this, so I'm thinking f from n to r, say, you can do it with c as well, where the sum of f of n squared is less than infinity, okay? So a perfectly good example is like 1, 1/2, 1/3, and so on, okay? This has a natural inner product, which is you take a sequence f and a sequence g, and you just go from the sum of f of n, g of n. Okay, so I realize all my formulas are essentially looking the same, okay? Maybe I'll just say this is less obvious than the last one. Okay, so what do I mean when I say this? Well, if I take the integral from -1 to 1 of f of x, g of x, okay, this is certainly less than infinity, okay, if f and g are continuous functions. All right? And the reason for that is, well, g of x would have to be bounded, so you can give upper lower bounds by just that bound times f. Okay? You take the product of these functions, it will have finite area underneath. It's not as obvious, right? So it's not obvious that fg, so if I just take two square summable sequences, why, when I take their product, do I get something which is square summable? Okay, so this is not obvious that f of g is in R. Okay, it turns out to be true, but takes a little bit of work. This is also something where p equaling 2 is special. Meaning if I looked at the functions from n to r, okay, where if I look now at the sum of f of n to the p is less than infinity, then this, you can try to do the same thing as above, and you will not get an inner product. Okay. And the problem is kind of precisely if you plug in f and f, then you're squaring, and somehow that forces you to look at square summable sequences. If you take some sequence which is like, cube summable or something, this will just spit out infinity. Okay. There's things that you can do with these LP spaces, but it's kind of L2 is the nicest one. All right. So that's another example. Let me give you just one more, which are if A, B are real matrices, okay, that say they're m by n, okay, then you can define the trace, or sorry, you can, skipped ahead, you can define an inner product on them to be the trace of B transpose A. Okay, so this is now a square matrix by construction. In this case, you can check that this is the same as the usual inner product on R to the nm. Okay, so just thinking of n by m matrices as an nm vector space and identifying them with R to the nm, the usual inner product there translates to here. Okay. So you can do the same for complex, okay, but then you have to replace B transpose by B star, okay, which is where you take the transpose plus conjugation, okay, so you take z to z bar for every entry in the matrix. All right, you can think of that's quite natural because when we had two vectors thought of as by n matrices, well, what we would do is take w1 conjugate up through wn, z1 up through zn, and then this produces the inner product that we saw above. Okay, so you can do the same thing with higher dimensional matrices, and again you'll get that's the usual inner product on C to the nm. Okay, so let me present now kind of the first really non-trivial theorem about inner product spaces. It's a fundamental property. The book has, I should say, if you go to chapter 5, there are a lot of easy corollaries that you get from properties 1, 2, and 3. But this is kind of the first significant step. So this is called the Cauchy-Schwarz inequality. Okay, so what this says is that if I take the absolute value of the inner product, it's less than or equal to the norm of one vector times the norm of the other vector. Okay, so for all x, y in the vector space. Okay, so you might have seen this before in R2 or R3 if you've seen the dot product. Okay, so at least in R2, it's known that the dot product is just x, y times cosine theta. Okay, so we're taking two vectors, and theta is the angle between them. Then all that this is saying is that this is sitting between -1 and 1. Okay, so that's essentially why it's true in R2 and what that's measuring. I should say you can also, people also write this, so I should emphasize you'll also see something like it's squared is less than or equal to the dot product of xx times the dot product of yy, and this is just bringing over the squares from the norm over to the other side. Okay, so let me prove this. I'll just do the real case, okay? The book will show you how to go from the real case to the complex case. Right, so let me give you the proof, which I think will kind of seem to come from nowhere, and then I'll give you the geometric picture, okay? So the proof is, well, you start with 0, we know that we can put any norm of any vector in V that we would like here, right? Because norm's always positive. So what we do is we put x minus y over the norm of y squared times y. So you can think at this point this is just the norm of some vector, right? And since I'm assuming, well, I should say y is not assumed to be 0, okay, otherwise the inner product would be 0 and we would be done. Okay, so this is well defined. Well, now this is just equal to x minus xy over y squared y, x minus xy over y squared y. Okay, and now by linearity this is xx minus 2 inner products of xy squared over y squared plus xy inner product of xy squared over y squared, right? Because I get the norm of y to the fourth times yy, which is the norm of y squared. All right, so therefore this is just equal to, so 0 is less than or equal to the inner product of xx minus inner product of xy squared over y squared. Oops, sorry, there should be a norm here. And therefore, bringing this over and then multiplying both sides by norm of y squared, we get that xy squared is less than or equal to inner product of xx times the inner product of xy. Okay? And that is exactly what we wanted to show. Okay, so this begs the question, you know, where does xy over y squared come from? Okay, so this is a perfectly reasonable question at this point. So let me recall something I defined before, which was that if I said the inner product of two vectors is 0, this was if and only if x and y are orthogonal. Okay? And so and the geometric picture, which I hadn't justified, was that the angle between them is 90 degrees. Okay? And you can see that if I took something like an R2 and I'm looking at AB cosine theta, then I get 0 here. Now, notice if I take any two vectors, okay, so if I start with any xy, now in just a general inner product space, if I define z to be x minus xy over the norm of y squared y, okay, which is precisely what we were looking at above, then the inner product of z with y is equal to 0. It's just pure calculation, right? You're getting, you know, you're looking at the inner product of xy minus this term with y. This is xy minus, xy, yy, which is y squared, over the norm of y squared. Okay, so you get 0. So in other words, if I go up here to the quantity that I was looking at, this is a vector that's orthogonal to y. Okay, the geometric picture in R2, which you can you know, check by using the definition of dot product involving cosine theta, or just computing, okay, is that this vector here, which I've translated so that it's orthogonal. So if I have x, y, then this vector is just, and I know it should be here, right, since it's at the origin, but it makes more sense to translate it so that it intersects y, is precisely x minus this inner product of y. Okay? And in general, you can think of the Cauchy-Schwarz inequality as measuring, how orthogonal x and y are. Okay? So in particular, if we go back to the inequality, if x and y are on the same line, this would be like the least orthogonal picture if you had x and y, and the Cauchy-Schwarz inequality becomes an honest equality, okay, if they're lying on the same line, okay? If they're orthogonal, then the Cauchy-Schwarz inequality is, well, the inner product is 0, so this is just the norm of x times the norm of y. In some sense, that's the largest it can possibly be. Okay, so that's what this inequality is really measuring in the general inner product space. Okay, and again, kind of the power of this statement is that it's true for all vector spaces, all inner products. Doesn't have to have a finite basis, could be infinite dimensional. Like so, the last example of L2 sequences, these sequences satisfy Cauchy-Schwarz inequality. Okay, so let me give you some corollaries of this, which I won't prove. It's kind of immediately computed from Cauchy-Schwarz. Okay, so the first is a triangle inequality for norm, which is something you might expect, right? If it's measuring the length from the distance to the origin, then the norm of x plus y is less than or equal to the norm of x plus the norm of y. Okay, so I have here x, y, x plus y. So this is shorter than the sum of these two side lengths. Okay, an equality if and only if they lie on the same straight line. There's also a parallelogram identity, which is useful. It says that u plus v squared plus u minus v squared is equal to 2 times the norm of u squared, plus the norm of v squared. Okay? This is saying if I take a parallelogram in R2, so maybe I should say this is the parallelogram identity, then we have u, v, and u plus v. So here's u plus v, u minus v. It's saying the sum of squares of these lengths is twice the sum of the squares of this side. Okay, so if this was a rectangle, this is essentially Pythagorean theorem. Okay, and in general, it's not too hard to prove from Cauchy-Schwarz. Okay. One of the main applications of it is it gives you a way to distinguish, or to say whether a space is an inner product space. Okay, so if you take any inner product, or in your product space, it better satisfy equality. Okay, so of course it better satisfy the triangle inequality too, and there are spaces that don't do that, but somehow this is a harder criterion to satisfy. So there are a lot of natural spaces with norms that don't come from inner products. I mentioned the sequences before, and this is the way that you can tell that these norms do not come from inner products. So maybe I'll just mention this briefly. Okay, so I'll say normed spaces, all right? So these are vector spaces with norms, okay? So there you can kind of measure the lengths, but you don't have inner products, and you can think inner products give you angles in vectors. So somehow if you just have a norm, you can measure the lengths, but you can't tell anything about the angles. Let me tell you the properties that we require. Okay, so we want a vector space. This norm function should satisfy, it should satisfy the triangle inequality, okay, which we just have above. Okay, so you can think it's not a linear transformation from V to R, but it's sublinear, right? If I take this the norm of the sum, it's less than or equal to the sum of the norms. It is multiplicative, so if I take the norm of CV, then I should get C times the norm of V, okay? Absolute value of C. And it should satisfy that the norm of V is greater than or equal to 0 and equal to 0 if and only if V is equal to 0, okay? So essentially what you get from inner product, but now you can define this without an inner product, okay? And then you get a more general class of spaces. So let me give you some example of kind of norms on Rn, okay? So we had some inner products on Rn, but now we can define just norms. So a natural thing to do is let P be in 1 to infinity, okay? We can define what's called the P norm on Rn, or Cn. It's defined analogously to how you define the norm induced by the inner product for P equals 2. So what you do is you just take x1 through xn, and you send it to the pth root now of x1 to the p up through xn to the p, okay? So you can do the same, actually, for sequences that are p-summable. Okay, so you look at things where the sum of f of n to the p is less than infinity. Okay, this works as well, and it just is a generalization. You can also set p equal to infinity, okay, which means that what you do is you take Rn to R, you take x1 through xn, and you just send it to the maximum, so the max value. I'll just say max of the xi's, okay? There's a similar thing that you can do for sequences. This also works for what's called bounded sequences. Okay, so I think this is, I'm just going to leave this as an exercise. I realize I haven't left many things as exercises before. But the thing, if you really want to understand a norm, what you really have to understand, so to understand a norm, what is this thing actually doing? You need to understand, or you should understand, the unit sphere, or the unit ball. Okay? So what is this? This just means the x in Rn, where x is equal to 1. Or sorry, the norm of x is equal to 1. Okay? Or x in Rn, if you want the ball, norm of x is less than or equal to 1. Okay? So I'll draw the p equals 2 case. In this case, you're looking at the unit sphere in the usual norm. Okay? And the unit ball would just be the filled in unit disk in R2. Okay, and you'll have a similar picture for R3 if you want to draw that, or Rn even. Okay? So the exercise is draw the unit norm ball for some choices of p, and in particular, kind of a good one to start off with is the max infinity norm. So you're just taking the maximum value. Okay, so what are the things that are distance 1 from the origin within this norm? Okay. So maybe I'll just mention one more thing. We can also, it's easy to check that for p equaling 2, p not equaling 2, okay? So if you don't have p equal to 2, these norms do not satisfy the parallelogram identity. Okay, so in other words, they all, none of these will come from inner products. They're just norms on their own right. Okay, so now that we are at the hour 5 mark, I think that's a good time to stop. So thanks. Sorry.